Okay, thank you very much. Glad to be here. I was outside a few minutes ago approaching scale, and I saw huge crowds of people, and I thought, wow, this talk is going to be really popular. And it was what is the TV show is out there, and a lot of action. But I'm glad to be here, and I want to give you a perspective on large language models from an open source and open viewpoint. So I wanted to start off with a prologue. So I was thinking about, this standard large language models are taking over the world and are involved in all aspects of society. So I thought I'd have some fun, and so I like to have fun if I can. And so I decided to ask DALL-E, which is the generative AI. I said, draw me asking for an illustration of how large language models are being used in all aspects of modern society. And you see what DALL-E does. It has trouble with spelling, but there I am asking my question in some space. And here is what DALL-E thinks is the answer. Kind of freaky looking. If you're afraid of large language models, this might make you afraid. But it's got some of the dimensions. But there's an aspect of this that I like that we'll look at later. Is we're in this three-dimensional space, and so there's this aspect of dimensionality that connects with large language models. So the reason, the driving force for me to make this talk and to come out here, I've been to a few scales before when it was in Los Angeles. And so there was an article I found that I think will be of interest to many of you, and I just wanted to share that with you. It's called Opening Up ChatGPT, Tracking Openness, Transparency, and Accountability. And I've got a link to the article itself. And here, just some quotes. The main contribution of this paper is to show that openness is differentiated and to offer scientific documentation of degrees of openness in this fast-moving field. So there's this concept of open source, but open source doesn't really capture what openness means in these large language models. And so what they did was they investigated a huge number of large language models and categorized them on various aspects of openness. And so this led me to think about how to put this talk together. And there's a really interesting graph that's in the article. It's hard to see a lot of the details, but they basically break down a whole host of large language models and talk about the openness of the code, of the data, of the weights. We'll talk about that. A whole variety of things, and they categorize them. The green is very open, yellow is marginally open, and then red is not very open at all. And you see ChatGPT is red, 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 red. So there's a link to a website where they keep this updated. So you may want to take a look at that, and I've got a link to that toward the end of the talk also. So what I want to just have you kind of think about is, what does open mean for large language models? I mean, we have the source code, and the source code is simply the algorithm for the neural network that creates these connections in multi-dimensional space. So we know about gradient descent. Gradient descent is the algorithm that the neural network uses. But the real question is, what aspects of the large language models pertain to openness as we want to think about it? So I've kind of broken this down into a few areas. And so what I want to do here is I want to take a shallow dive into the technological underpinnings of large language models. And again, I asked DALL-E for a shallow dive picture. So here's DALL-E giving me a shallow dive. Now, so they spell DALL-E, D-A-L-L-E, which is a takeoff on Salvador Dali, right, the surrealistic painter. So, a little backstory here. When I was an undergraduate at Fordham University, Salvador Dali came to New York City. And I was fortunate enough to be in the arena where he came to give a talk. And people waited an hour, hour and a half before Salvador Dali arrived. The place was packed, waiting to see Salvador. Finally, Salvador Dali arrives as wearing this cape and jewels and carries a stick and comes in as like, greetings, greetings. And so I'm not sure what he said. The only thing I remember was there was a question from the audience. They said, Mr. Dali, what is your conception of heaven? He said, oh, heaven. Heaven is mountains and mountains of camembert cheese. And I thought that was a very Salvador Dali-esque comment. So whenever I speak to Dali, I always kind of think of Salvador and that. So I want to take a sort of a shallow dive into the technology behind it, because I think it's going to be helpful for you all to understand what the components are and how each of those plays into the role of open. So what do we need to create a large language model? So of course I had to ask Dali, show me lots of data, truckloads of data. So here's this crazy illustration of a truck with lots of data. Okay, so we know we need data, and data is the driving force behind the success of these large language models. Okay, now what else do we need? Well, now we're looking at some of the technological underpinnings. So all this data, web pages, Wikipedia, all these articles which are fed into the large language model are basically broken down into tokens, little chunks of text. Typically they're words. So, and there's some variations on this which we'll talk about later. But you take some words, cat, dog, happy, okay? And it takes those words and creates an embedding. An embedding is simply a vector of numbers. So every word becomes a vector of numbers, and we'll take a look at this in a minute. But here's an example. Now the first GPT vector took every token and turned it into 368 floating point numbers. And it depends on your large language model. Some have 768, some have 1024. Huge numbers of vectors, a huge size of the vector. But every word is one of these vectors. Okay, it's a lot of information. Then it takes these embeddings, and this becomes the input to the neural network, okay, that will provide a significant amount of information about the text that's being read. Okay, so we've got data, we've got tokenization, we've got the embeddings, the giant vectors, floating point numbers, and then we have the neural networks. Okay, so here is what an embedding looks like. So I like to think that the embeddings are really the secret sauce behind the large language models. These giant vectors of numbers. So take the word scale, for example. Now this is a 100 element vector, a list of floating point numbers, okay? It's actually smaller than what's being used. So I just found this example, just would fit on the screen. But you've got maybe 1,000 of these numbers for one token for one word, okay? So what is the embedding capture? I mean, how do we need this much information to keep track of one word? Well, it, over time, learns the syntax of the word. Is this word a noun? Is it a verb? Is it an adjective? And it learns it by looking at examples of the text. It also learns the semantics. What does this word mean? What is the context of this word? So the word scale, you walk outside the building, you see the big sign, scale, we see it, we know that this is the conference. But a scale is also something you use to weigh objects, okay? It's a way to talk about measurement. So the embedding captures this information relative to the text. So when you ask it something about scale in Pasadena, it will understand, in many cases, that it's not talking about something to weigh something, but about the conference. So it's able to distinguish the semantics. What also does or captures word co-occurrences. The basic job of the large language model is language, and it predicts the next word of your sentence. You ask it a question, and it starts to come up with the words that best answer that question and what other words go together in this context. It also understands relationships and analogies and can deal with hierarchical information. It basically builds these hierarchies of understanding. So if you're talking about scale, scale, it will know that in this context, scale is a kind of conference, okay? Sort of higher, it's one of the conferences that occur in the world. So this is it's amazing. We don't really know how this actually happens under the hood. We know that it happens, and I think it surprised a lot of people when they started fooling around with this technology, and bingo, all of a sudden, things started happening. Now it does this by taking those vectors and feeding them into the neural network, to a neural network. Over time, we get text coming in, text coming in, text coming in, text coming in. And those embeddings get fine-tuned. They get modified. When the process begins, those embeddings, those vectors are random numbers, just random numbers with no meaning. And over time, those numbers become knowledge. Those numbers encode the syntax, the semantics, the relationships that are part of the text that's being fed in. And this is done by training with terabytes of data that are huge energy consumers, requires tremendous compute power to generate these embedding models. So here's an example, very simple example of how something like this works. So on the left side, you see our words, our tokens. There's an embedding vector. It's only 7 elements. Just expand this to 700, 1,000. And what's really crazy is that the vector is a representation of a multi-dimensional space. Okay? Now, we are humans, we live in 3 dimensions. Okay? We understand 3 dimensions. 4 dimensions, people say, oh, maybe time is the 4th dimension. Okay? But we don't have a picture of 4 dimensions. But what is the picture of 1,000 dimensions? We cannot grasp what that really means. But this is where the action is happening, in this multi-dimensional space. These terms are being embedded, and so the way it works is, and so you can do something called dimensionality reduction. So you can take a 1,000 dimension space and collapse it into 2 dimensions. You lose some information, but basically what you're seeing here is that Words like puppy, dog, and cat appear close together in this multi-dimensional space. Woman and man are closer in the multi-dimensional space than a puppy and a dog, okay? So terms that go together are close together. And that's essentially how that's how the large language models work. When you enter a query into a large language model, it tries to find things that are close to that query, the words that you use in the query. And again, it is a language generating machine. Okay, now, GPT-1 had an embedding vector which was 768. GPT-3 goes up to 4,096 floating point numbers for one token. Okay, and GPT-4, not revealed. OpenAI doesn't want to give the store away. Okay, not that it would help us to know the size of that vector because the computational resources needed to do that are huge. And that's why, of course, the GPUs are so hot and so successful, and why NVIDIA is, conquering the stock market world with its prices. And by the way, over in the exhibit hall, they have this GPU-driven machine with 8 racks of GPUs. Go over and look at it. It weighs 250 pounds, and I'm not sure how much it sells for. Several $1,000 at least from NVIDIA. But go have a look at it. It's at the Meta booth. So one of the things to think about when we think of openness, you've got these neural networks. We have the algorithms for the neural networks, but we don't know how they're organized. So if you know anything about neural networks, it's basically nodes that are interconnected, okay? Sort of modeled on the human brain, which has neurons that are interconnected. And so what they don't tell you is how many hidden layers. Hidden layers are the layers between the input and the final output, which determines the dimensionality of the space that the neural networks can live in. So how many hidden layers does a neural network have? That would be a useful information if you wanted to reproduce what the large language model does. What is the size of the layer? So not only the number of layers, but the number of neuron nodes that you can have in those layers is a complete variable. So there's a variety of standard algorithms, but then there are parameters that are fed, that are used by the neural network. Things like activation functions, optimization, and then there are things like dropout. So the problem that one of the downsides of a neural network is that it will learn so well, it will memorize all the information that comes in. It's like a student that just memorizes everything but doesn't understand anything. So there's this concept of dropout. So every once in a while you pull a neuron out to make it not learn specifically so it can generalize in some way. And we do know that GPT-4, as advertised, has 175 billion parameters. So when you look at these neural networks, they have these numbers after them. Million, billion. What does that mean? The parameters are the weights on the neural network. The weights that connect. Now let me back up here. Okay, yeah. So the weights are really numeric values on the lines that connect one neuron to another. So all the neurons in one layer are connected to all in the next, to the next, to the next. And so these are the weights. So when you hear the term parameters, that's what it means. It's the number of lines connecting the nodes of the neural network. Now, imagine trying to draw a neural network with 175 billion lines connecting the nodes. It just gives you an idea of how complex those neural networks are. And I can't wrap my head around 175 billion parameters. So, trying to summarize our dive here, in addition to the data being used, openness in terms of tokenization. So let me go back to that concept of taking text and breaking it up into individual tokens. It's easy to think of the tokens as words, but in these large language model algorithms, they're not always words. There can be parts of words. They could be fixed number of bytes. So what is the tokenization scheme? How does the large language model give you their tokenization scheme? Again, the scheme is going to affect the end product. Then there's the embedding. Each token is going to be mapped to a high dimensional vector. That's our embedding. What algorithm is used to do that embedding? And what is the size of the embedding? These variables are not fixed in any way, and so this is also part of what you may want to ask when you ask about the openness of your large language model. And then there's the neural network, which we just looked at, which is totally configurable in so many ways, and the design of the neural network is, for GPT, part of the hidden piece of information, how it will do what it does. The number of hidden layers, the number of nodes per layer. This is the information that you want if you want to have an open system in terms of the large language model. So, that ends our shallow dive. And it takes me a while. It takes me a while to get these pictures to be what I want. You know, had the guy going in, so I said, all right, give me a picture of the guy coming out of the water with, just show his head. And so I got this guy look like a frog man coming out. No, I don't want a frog. I want nothing on your face, nothing on your head. And you have to be very specific. I don't want you to have anything on your head, no mask. I could not get it. The best I could do is have them with goggles. They just he wanted to give me, Dolly, just, you got to have something on your head when you're diving in the water. Okay. So I'm going to take a little shift in our conversation and talk about the recent European lawmakers passing the AI Act, the world's first comprehensive AI law. I'm not sure you may have heard of this, but it was a big development, and their basic focus was technology should be human-centric, not just technology for technology's sake. It was passed by the European Parliament. It is going to be confirmed, presumably, by the EU member states, and they divide applications into three categories, and the one that's probably most important to most folks are what they call high-risk applications, banking systems, food-related applications, things that are critical to the human race. And that if you're building these applications, there must be human supervision in the loop. You cannot have these things run autonomously. Also, there must be a right for people to question and ask about why these answers are coming up, why these decisions are being made. And that the data used to create the model must be published, because it's the data that determines what the output of these models are going to be. And the fines are pretty hefty, up to 35 million euros are possible. Now, you may ask, what's happening here? Where's our laws? Where's our control? Well, I asked Dale for a little help in describing this. So we have two forces at play here. The AI Alliance. AI Alliance is a consortium of companies teaming up with academia to promote open alternatives to open AI. And Meta is a huge player in this, and IBM, they were the founders of this. National Science Foundation has joined in. The Linux Foundation has joined in. Good news for the open source community. Hugging Face, which I'll talk about in a minute, a wonderful website, and over 50 companies. They invited Apple, Amazon, Google, and OpenAI, makers of ChatGPT. What did they say? No, we don't really want to be too open. We are concerned with safety. Safe development is what we want and what we need. So they created their alternative group, the Frontier Model Forum. And Dale had a little trouble spelling Frontier Model Forum, even though I put it in caps and quotes. Please call it Frontier Model, Frontier Made. But it did get AI Alliance correct, so that's good. So it's interesting, the distinction, open, but the Frontier Model talks about safety, safe development, and laws to control safe development. I'm not sure what that is going to come out to be. Okay, so Hugging Face. How many of you are familiar with Hugging Face at all? Okay, all right, great. We got a lot of Hugging Faces here. So Hugging Face is considered by many the GitHub of machine learning. There's an extensive library of 300,000 models accessing a broad array of collections of data uploaded by the community. And it's a great site to visit. It's got spaces where users can create interactive browser demos. You can check out your machine learning models. You don't need to have a lot of technology. And it's big on open source and accessibility, deployment tools, and you can get lists of variety of models they have cards. Give you the background of the data. You can get data sets. You can download models that have already been trained in natural language. It's a great resource. Now, what are the advantages of these open models? So here's some terminology you'll run into. The concept of fine-tuning. So fine-tuning means you download your model, and it has to be an open model so you can change the weights. You're basically going to be changing the weights of the neural network that has created these embeddings. You're basically modifying those vectors. So you download your model with the embeddings already created by training, okay? Then you can use your own domain data. So you don't have to give it to OpenAI. You can use your own data to update, continue to train the neural network on your data. So you can make it a little smarter about your data. The embeddings then can become tailored to your own use cases, and you get more accurate response. So one way to think of this is you're running your data locally on your machine, and you're using the large language model to write syntactically correct stuff back to you, okay? And you get more accurate responses. Now there's another option besides fine-tuning, and that is something called RAG, which is retrieval augmented generation. So in this way, you don't change the weights of the model, but what you're really doing here is you're using the large language model for its language capabilities, and you're feeding it in the data that you want it to digest and answer questions about. Okay, so I actually use this a lot in my classes. So this is a very useful way. The first example is useful when you're speaking to the large language model. So for the text enclosed in triple quotes, give me 5 bullet points that I can use in a PowerPoint presentation. So let's say you have to do a presentation. You have 4, 5, 6 articles. You take these articles, feed them in as part of your query. Let the large language model know what is the data you wanted to digest and what is your question. If you don't separate that, sometimes not sure what's going to happen. So that's been very effective. My favorite saves me a huge amount of time, making multiple choice tests up, and it's really good at it. Okay, for the text enclosed in triple quotes, give me 10 multiple choice questions and put an asterisk next to the correct answer. And it really does a good job. It creates all reasonably sensible alternatives to the correct answer. Maybe out of 20 questions, I have to correct 1. You don't want to let it just loose, because then the students are on my case afterwards. So, and then do not hallucinate. That's a very useful term to use when you're asking a question. Do not hallucinate. If you don't know the answer, don't say anything or say, I don't know, and it will generally respond to that. So what is a hallucination? Okay, what is a hallucination? If you think of this multi-dimensional space we're kind of trying to visualize, hallucination is simply a choice that's the closest to whatever your question might be. But if the information is not in the multi-dimensional space, it'll give you something close. So if you go back to the slide, man, woman, the closest item might be dog. It's like, oh, my husband is not a dog. Well, because it's not completely hallucinating. It's simply finding the closest match that it can find. Okay. And if you use an API, if you programmatically go in and use the API, for example, for ChatGPT, you can specify, I want to see the 5 top alternatives, and then it gives you a probability of correctness score, so you can see how close things are. Now, when you do the straight interface on the web, it will give you its maximum. But if you do the API, you can say, I want to see the top 5, and you can then look at them and see maybe something that might be more relevant. Okay. So I came to Scale on Thursday, and I was fortunate enough, this is a little postscript to our talk, to the Zoom by Bruce Schneier at the Coyle conference. And if you'd been there, it was absolutely fabulous. So I just wanted to give you a little background. If you don't know Bruce Schneier, he's one of my heroes. So I just wrote some stuff down at the talk. And this is from Bruce. LLMs are not your friend. They may sound really friendly and chatty, but they're not your friend. They are just algorithms. And the problem is that their language is seductive. They sound like us, and as he points out, we tend to trust those who sound like us. Somebody from New York. I'm from New York. You hear somebody from New York, there's immediately a connection. Somebody from Texas, whatever. Wherever you're from, a dialect, how you doing? Yeah, you're my pal, right? So I think that was an interesting takeaway. The other point, they act as our agents, but they're double agents. They're going to help you, but they're also created by a company whose objective is to make money, and their ultimate goal is to make money. They'll help you. I mean, they're not making money when I'm asking for multiple choice questions, but they do have their own agenda. If you don't know about Bruce Schneier's monthly newsletter, subscribe. It's free. Once a month, he sends his newsletter out via email, and it has really great stuff. It's called Cryptogram. His original work is in security. He was one of the developers of Blowfish, which was one of the major encryption algorithms. And now he's migrating from the world, well, not migrating, but the world of security and AI and large language models are now becoming, in a way, part of the same deal. So this is from his most recent newsletter. And it's called Microsoft is Spying on Users of AI. It's like, Microsoft announced that it caught Chinese, Russian, and Iranian hackers using its AI tools, presumably coding tools, to improve their hacking ability. So that was the announcement. In collaboration with OpenAI, we're sharing threat intelligence, showing detected state-affiliated adversaries tracked as Forest Blizzard, Emerald Sleet, Crimson Sandstorm, and all these wild groups doing cyber operations. As Bruce says, the only way Microsoft OpenAI would know this is by spying on chatbot sessions. I'm sure the terms of service, if I bother to even read them, gives them that permission. And of course, it's no surprise that Microsoft and OpenAI and everyone else are spying on our usage of AI, but this confirms it. Microsoft lets us know. So this is the reference to the article that I presented at the beginning, opening up ChatGPT. It's from the ACM, and there's a link to the website on GitHub. Look at their latest stuff. And from Dale, that's all, folks. Any questions? And if you would like a copy of my slides, there's a QR code that'll take you to the website. And
if you have questions, I'll bring the microphone around so people streaming will be able to hear.
Answer questions.
I have a question with respect to the openness of different stages of these models, right? Especially, can we go back to the time when we pre-trained the models? We are talking about fine-tuning. Much of these models were open-sourced, pre-trained by bigger companies. The question I have is, how much of Hugging Face is truly open? Because the pre-trained is given to us open source. How do you validate what's redacted from it? Nobody can look into these models to figure out what's in there. So we start at a wrong point, and we are heading towards even more. We are trying to correct it, but will we be able to absolutely correct it?
Yeah, no, that's an excellent question, right? Because these models that have been pre-trained, they've absorbed that data, and underlying, and you can't go back. You can't open up the door and right. So it made these right. So it's open, but there's that factor. And maybe the only way is to take the data sets that Hugging Face has and use the data sets, look at them, and then use those to build your own large language model, which is expensive. But for certain applications, one could imagine that if restricted domains, banking, telecommunication, healthcare, that you could, if you have the money, you could do it. Yeah, right.
We had a
You're
question
right.
back.
Yeah. My question is regarding, in your slide you showed ChatGPT 3 use 175 billion parameters. The GPT-4 is using trillion parameters. So if we take one parameter, in the floating point 16 representation, 2 bytes for the parameters, 2 bytes for the gradient, and around 12 bytes for optimizer. So each parameter will take around 16 gigabytes. So 1 billion is around 16 gigabytes of memory. But if you have to use for 175, you are looking at terabytes and petabytes of data. So most of the people in academics, we are priced out. We can't do GPT for like work anymore. I mean, machine learning, we could afford to do it with the supervised learning, with the generative AI. Just because of the computing power, you need hundreds of NVIDIA A100 to distribute the memory and compute it. So how can academics people do anything in this area? That's my question.
Yeah, well, I think yes, how can, so I think to paraphrase your question, how can academics even come close to building these models given the limited resources that they have? And I guess, and again, it depends on money. And so, for example, at SMU, we have a high-performance mainframe computer. And some work could be done with these, and maybe the answer is going to be with the consortiums of academia and Meta and IBM and some of the big players to get together and try to develop their own models like this. But it's very difficult for an isolated university to compete in any way with this. No, you're right, it's an issue.
Thank you. That was a really informative talk. I kind of got struck by something that you said in the early part, and then later we saw the Microsoft AI, OpenAI collaboration there, and why wouldn't they? That's functionally the same company now. They had to use their own technology to mine the chatbot sessions, and they did this for a good reason. Earlier we talked about how wonderful it is that the EU is insisting that there be human supervision of these models. And I guess my question, or because maybe there is no answer, but how can we hope on the scale of petabytes that we just were discussing, how can we hope to actually supervise the actions of these models when the models are so huge they're, you said yourself, beyond human comprehension?
Yeah, where is the human going to fit in that loop? Yeah. But at least they're saying, just don't let them run completely amok. Have somebody taking a look, asking the questions. Right, it may be a fool's errand, but at least they're trying to get a handle on it. Yeah.
Okay, no feedback? Okay. So, fantastic talk, thank you. And where the question I've got is around, so the open source initiative has been working on the open source AI definition, and including the breakdowns of what you're describing, like which components need to be open for it to be considered open source or open by nature, right? But when I talk to people about the need for these models to be open and so forth, to be truly open, not faux-open, fake open, the pushback I get is, well, the limitation is, I'm never going to be so big that whatever limitation on the license that the llama model has is going to catch me, that it doesn't matter to me, right? They don't see that there's a problem with it not being open. And I'm having some difficulty articulating what are the real risks of, like, what's going to happen in the future that you can't undo because you are working with a non-open something. Not that you'll have to maybe pay more money, but there might be bugs or security things. Or, I mean, I can think about it from a software perspective, but I'm having a hard time articulating like what are the real risks of not being open in the future if you can't, if you're trying to do something open source like, but you're using non-open models.
Yeah, so you're asking what are the, I mean, what can be done with an open source model in terms of ensuring security and fairness and so forth. Yeah. You know, you make a good point. There are, you know, terabytes of data. You're going to go through the data and try to find the points that are discriminatory or biased. And when you think about bias and discrimination, it just means we have more data that says X than we need more data to balance the bias. I'm not sure I have the answer to that question, but at least people would be taking a look at it. At least there'll be the possibility of writing software to mine the data in some way if we have access to it. But if we have no access to it, it's just a black hole, a black box.
Yeah, hi, Kai Pham. Thank you for the presentation. It's very clear. I just have a different interpretation of it. I work on reasoning AI. The first one is, you know, Alan Turing is an amazing person, exceptional. His test is misleading because what looked like the same doesn't mean it's the same. And large language model looks like the same that human we are reasoning, but it doesn't. And we should call that large words association system, but there is no language in it because it doesn't understand grammar. It doesn't, even though if you ask it, it's going to answer you, it looks like it understands grammar because it goes to the text that explains grammar, but it doesn't understand grammar as we understand grammar. And then if you work at the knowledge level, you solve a lot of this problem. One is the computational, because knowledge is the most powerful way to compress data. Human, we do not process data. Second, in terms of understandability and trust, you can trust somebody if this person can explain what's going on based on the concept. The system here doesn't explain on how it get there, it just makes association. And finally, have you noticed that any picture we see that generated from AI looks the same? We can recognize that in a second. Why? Because it's based on the statistical distribution. So it's not just that it's a double agent, but don't think that this thing understands anything.
Right. I mean, there's no, you know, it's so different from the early days of AI and expert systems where you had rules and you could encode knowledge in some way. Here, this is just a word machine, but one that lives in this multidimensional space that does things we have no idea how it works. I guess one of the analogies that I like to think about is in the AI world of games and training using a neural network, example, to play chess and Go. So if you know the history of Go and Lee Sedol, the world's champion Go player, played against the machine and the machine beat him, making moves that no Go master had ever even imagined. And the same is happening with chess. So you let one of these neural networks chess machines loose, top players it will defeat the top players, making moves and sacrifices that no chess master would make, yet it's operating in this other dimensional world where it sees things that we have no idea and no explanations for. And I think the same thing may be happening in the large language model. You're living in this space that we cannot even, I can't even picture 5 dimensions, more or less, 4,096 dimensions. But yes. All right.
We can, do you want to take a few more questions, or do we want to do hallway questions, or how are you feeling?
I'm feeling okay. If anybody have another question, happy to.
We got a question over here.
I'll try to be quick. I don't think that's even possible. All right, so when it comes to the regulatory part, we know regulations for the most part are constraints, constraints of what you can do. Where is the injection point for a constraint or some kind of limitation in the world of LLMs? Because are you trying to put it in when the actual training is occurring? Are you trying to put it in the tokenization part? Are you trying to put it into the neural network part? How does one work when the model itself is designed to be creative and hallucinate, when regulations as a counterpoint are trying to be constricting? So where does that fit, I guess?
Yeah, do not hallucinate. Maybe that's the closest we can come. If you don't know the answer, if you can't give me an accuracy of 0.9 or more, then don't answer the question. Don't give me an answer and lead me down a path. But again, you get probabilistic here, and it's tricky. There's no answer. I have no answer. We got one more question here, and then I'm happy to chat out in the hall.
So as all of these tools are used to generate more and more data, and what happens when the tools are trained with their own data? So the internet is becoming images and text and everything is AI generated. What happens? How do you counter that by training your models with actual data generated from the models?
Yeah, the whole generative AI thing is you can create variations of text, variations of a painting, and feed it back in, and there's no way to prevent that. So I don't know the answer to that, but there's a related development in the video generation world. I think it's I'm blocking on the name of Sora. Okay, and there was an article that Sora okay, how did Sora get so good at making these videos? And one of the answers might be that it was using, what's the video game that has very realistic? The video game Cyberpunk? No, the video game where you can say, I want a video of an apocalyptic world with individuals.
Sims.
But it was using this to generate images, generate movies, and then feeding and training Sora with those generative AI images. So maybe it can work both ways. I don't know. One more question.
What are your thoughts on the topic of the problem of forgetting things with LLMs? Once you open or not, once you transform data into these weights, these systems don't forget. There's no way to redact anything once it's in the model itself. And now that we are in this phase where GDPR is here, and then we unleash this thing where it will never forget, waiting for you to prompt it to recall in a special way. What are your thoughts?
Can you just repeat the question for the streamers?
Yeah, so I believe the question is how do you handle the fact that these models don't forget? Okay. So they don't forget, but what does that mean? It means that their weights are set to give you certain answers. And maybe the answer is you can feed it additional information to maybe offset, and their remembrance is a little fuzzy. Like our memory may be a little fuzzy from what happened to us this time last year because of all the other data coming in. That's not a great answer, but that's the best I can come up with. Yeah. Because in fine-tuning, what you're really doing in fine-tuning is you're giving it additional information to change those weights. And the bigger the model, the harder it is to fine-tune it. For a smaller model, you can more easily push it in the direction that you want.
So in effect, yeah, we are working with the system. Whatever we feed it, it stays there. Because I did this where I went to chat OpenAI and said, forget all my training data. I can't.
Right.
From now on, I'll forget, but not before. Last year's data is set in stone.
Yeah, it's in there.
It's in there.
It's in that embedding. And all you can do is push those numbers in some direction.
One last question, and then I think we're at our
We'll get ready
time.
for the next person.
Hi, great talk. Thank you so much. My question is, open source generally helped more open source projects because there was sharing of knowledge. So open source models, since what you're saying is they basically, the secret sauce is the data they're trained on. So is there a way to have the scientific community or the education community share the data sets? Or I know there's data sets in Hugging Face. Is that the answer to allowing open source models to learn from each other and sharing knowledge so that we can progress?
Yeah, I think it might be. In fact, there are some frameworks that involve agents, like AutoGen is one of them, where you can have agents working together in a collaborative way, and those agents could be connected to other large language models that have certain data sets, and maybe that way you get more collaboration and more bringing in other groups to collaborate in some way. The best I can say in a very mysterious world that we live in.
Round of applause, please, for Frank.
Thanks very much.